Hey guys, we are going to talk today about something called valence shell electron pair repulsion, or better known as Vsepr. And it's all about the shapes of molecules. So the theory behind Vsepr is this, that you can predict the shape of the molecule based off of non-bonding electrons and bonding atoms. So you find the shape as atoms sort of fit into different spots. So the shape is determined by the number of bonding and non-bonding electrons in the molecule. These are what are called domains. Domains. So there we go. Now that I got a pen. D. O. N. A. N. S. You're going to hear me use that term over and over and over again, so it's really imperative that you understand what I mean. In order to determine the shape, you must first draw the Lewis diagram. So, treat multiple bonds, whenever we're drawing the Lewis diagram, treat multiple bonds as if they were one domain. So, here are the overall structures. So A in any of these is going to represent the central atom, X is going to represent a bonding atom, and E is going to represent a lone pair or a pair of non-bonding electrons. So these are right here, these are our domains. I'm just going to write D because the drawing is a struggle. But however many bonding atoms plus electron, unpaired electrons, when you add those up, that should be your domains. So this is the basic overall structure. So let's look at some of the shapes here. So if you only have two domains, right, or two bonding pairs, you'll have what's called the linear shape. If you have three domains, you'll have what's called triangular planar, or more often trigonal planar, and your bond angle of 120 degrees. So let's look at, for instance, CO2, O, C, O. We'll have a linear shape. Hang on, let me get the double bonds in there, right? So this carbon right here only has two domains, or two areas where you either have lone pairs or you have bonding happening. You've got a domain here on the right and a domain here on the left. Okay, so the number of domains is 2. So the bond angle, or the angle between this domain and that domain, is going to be 180 degrees. So here is an example. So this is just a small, this rotating molecule here is just a small model of what carbon dioxide would look like. And it's just got that linear structure here. So the next type is called trigonal planar. Now this is what we would sometimes call the molecular structure, because we're talking specifically about how many domains you have. Now it's going to look kind of weird here. Where'd my pen go? If I were to draw SnCl2, good, it stopped here. Off here would be another set of electrons. It's an electron cloud, and here are your two electrons. Let me draw those in a little bit. Right, but when we draw the actual molecular structure, we don't include them. So we have 3 domains total, but only 2 bonding domains. But even though, because we have 3 domains total, our electronic geometry, or EG, is trigonal planar. Now, if you remember what I said, if they are thick, that means that these are coming out of the frame of the board, whereas these dashed ones mean that they're going behind the board, or in this case, the screen. So let's continue. Here you go, BF2 is 180. BF3, there's that 120 degree angle right here that we were talking about. There you go. Molecules with central atoms surrounded by 4 bonding pairs is called a tetrahedral. so that you have your tetrahedral shape. Now, we made this when we made methane in class. The angle between each is 109.5. All right, so notice this one's coming out of the board. You have one chlorine that looks far back in there. You get this weird sort of tetrahedral shape. The easiest way to do this is make a three-dimensional model, but the angle between these two right here, as shown, is 109.5. So let's talk about water, for instance. If you were to draw water, here's oxygen, and it's got its two hydrogens. Hydrogen, hydrogen. Right, and it's got 2 electrons here, 2 electrons here. What you end up getting is a bent shape for oxygen and 2 sets of lone pairs. This has 4 domains. Here's a domain, here's a domain, here's a domain, and here's a domain. So for water, its electron geometry, again, is tetrahedral. All right, we're going to talk about molecular geometry a little bit later. So there you go. So here's, again, our non-bonding pairs, just like I was showing you. So you get something called trigonal pyramidal. Okay, and trigonal pyramidal is a molecular geometry. Okay, so now this right here is molecular geometry. Mg is trigonal pyramidal, right? It's a triangular pyramid. Its electron geometry is tetrahedral because it has 4 bonding domains. You've got that extra set of electron clouds just out there that's pushing the sides of the molecule down. Okay, so it's pushing those hydrogens down to make that triangular shape. And so you get a molecule that looks like that. When you... sorry about that. Phone calls. Okay, so the same idea. Molecules that have a central atom and they have 2 bonding pairs and 2 non-bonding pairs still have that tetrahedral electron geometry, or electronic geometry, but their molecular geometry is called bent. So remember how I was telling you about water earlier? Here's that water again. So it's a little bit smaller than 109.5 because these electron orbitals, these lone pair orbitals out here, are really, really big. Oh, that was a fail. They're really, really big. So they're really pushing down even further in order for you to get this shape. So this, its Eg, is tetrahedral. Too bad these aren't touch screens. I'm just going to put a T for tetrahedral. But its molecular geometry, in this case, is bent. T. You can read that, right? Yeah. So bent. So here are all the possible things for tetrahedral. These are all, its electron geometry is all tetrahedral, right? But here, right on this one, we've got tetrahedral as its molecular geometry as well. Here, its molecular geometry is trigonal pyramidal. And here, down here, even though my face is in the way, let me see if I can move this. Here, its molecular geometry is bent. When you have 5 bonding areas or 5 domains around your central atom, things start to look a little different. So this is where you're in those 3rd period elements. You can break the octet rule. So you get what's called trigonal bipyramidal. So it's 2 pyramids along the same base. So you're going to have 2 bond angles. I'm sorry you can't see this down here, but the base will be 90 degrees. So between each of these, you have 3 right here. Those 3 will each be 120. This one right here will be 90. All right, and that's, again, its drawing right there. I'll move again. Okay, So its electron geometry and its molecular geometry right now is trigonal bipyramidal. Trigonal for the tri, bi for two pyramids. Right? Here's my top pyramid. Here is my bottom pyramid. Here are all the different things that you can get for trigonal bipyramidal. Okay, so this right here, its molecular geometry is trigonal bipyramidal as well. Here, this is what we like to call a seesaw shape. Kind of looks like a seesaw. You could rock back and forth on that. This right here is called T-shaped. And this down here is linear. When you have 6 atoms, okay, you get octahedral bonding. All of your bond angles are 90. So here, any bond angle you take, you're going to get 90. All right, so you get this very different pyramidal shape here. All right, let's see. So here are our possibilities. Okay, so right here you have octahedral. Couldn't tell you the name right now for this because that's what is the name for that? Hang on, let me go look it up. It's called square pyramidal. I knew that. This one right here is called square pyramidal, and this one right here is called square planar because it's falling in a plane. Okay, and that's it. So yeah, so let's look up some stuff here on Google because I'm going to give you this chart. It'll be on the website, but let's at least, no, I don't want to keep those. Let's at least look some stuff up here. Let's see, molecular geometry chart. Yeah, let's do that. And so here's my molecular geometry chart. And you'll have a copy of this. Come on, just give me the chart. Ugh, never mind. Molecular geometry chart. Oh, wait, I see it, PDF. Alright, so here is our PDF, our molecular geometry chart. So it says groups of electrons. Right here I would change this to domains. If you can. I can't because it's a PDF. But if you want to, this will be up on the website, but if you want to cross that out and write domains, that will help you a lot. So if you are looking and you've got 3 domains, but then you have one pair of non-bonding electrons, then you can see here that that's, sorry, I'm like pointing at my screen like you can see it. If you only have one set of unbonding electrons, then your electron arrangement is bent. And so you can see that here. And you'll get slightly less than 120 degrees. And so this chart really just helps to sort of lay out what your electron shapes are actually going to be. And in all actuality, it ends up being very easy, and at least I think very interesting. So that's it. So let's see. You guys, we're going to go over these molecules in class on Monday and Tuesday, and so we're just going to spend some time modeling and just playing around with models. But here's what I need from you. I need to see a set of notes from you with images showing these shapes. Now I'm also going to load the guided notes up on the website, so you should be able to see them there if you want to print them out or if you want to put them in your own notebook. But both the guided notes, the PowerPoint that I just showed you, and this chart that's right behind my face right now is all going to be up on the website. So, good job.